In section 6.4, we're going to look at a new method for analyzing a truss called method of sections. Now, since our truss is in equilibrium here, it's not moving or anything, we can slice it into sections and analyze it locally. For example, say I want to find the internal load on, let's see, GC. So the force in GC. Well, I can take a slice here of our truss, say section AA, and redraw our truss with the forces on the portion that I've cut here, but the rest of this, these members are cut, and I'm just going to represent in this free body diagram here the forces. So this is force BC, force GC, and that's what I was interested in, was GC, and the force GF, pointing at F. So I can then use my equations of equilibrium and analyze this structure drawn as this free body diagram. So for member GC, if I'm going to look for that first, what I could do is I could sum forces in the y direction on this, set them equal to 0. I'm going to get, let's see here, we have angles we can stick on here. So these angles are 45 degrees, since these are all 2 by 2s. And that means I'm going to have something like force in GC times sine of 45 degrees. That's in the positive direction, so I'm having positive, and I subtract 1,000 newtons off of that. Now notice I drew all my forces on my internal members in tension, and I just put the load on. Notice the section that we caught doesn't even include the reactions. I'm still getting values here. So F of GC here is going to equal 1414 newtons, which means it's positive. That's going to be in tension. I could then continue on here, analyzing other pieces. Here's GF. Let's analyze GF now. Or better yet, let's do BC. Analyze BC. So to analyze BC, I could just sum moments about G. Set those equal to 0. Since I'm doing this whole structure, we've got moments. So I've got 1,000, and that has a tendency to rotate about G in the positive sense. And then I have minus force BC, which is going to tend to rotate in the negative sense, and that's a distance of 2. If you look up above, you'll see that's a distance of 2. So these cancel out, right? And we end up with just straight up just F of BC equals 1,000 newtons. That's also in tension. Let's get that last force that we have in here. Let's see here. So if I want to pick up this force, This force is pointed at C. C is not really located very well here. C is really more over here. But this force points at C, and this force points at C. So we can take them out of the relationship and just sum moments about C here. So moments about C equals 0. And then I'll have 1,000 times 4 and then FGF is also rotating in the positive direction, and it is times 2. So FGF equals, well, it's going to turn out to be negative 2,000, right? So that means FGF is in compression, and these other two members are in tension. So let's say this truss is symmetric here, and the distances here are well, yeah, I guess it's okay. Here, wait a second, let me draw this a little better. Here's the dimensions. Got 30-degree angle here. This thing is symmetric, so it's 2 and 2 and 2 and 2 here. So that would mean that this must be 60 then. We can this distance here, this angle's 30. So let's analyze this and find. Let's find F of EB, the centerpiece. Now, the way this is drawn, there's a lot of zero force members in here. But what we're going to do is I'm going to add loads here. So we got 1,000 pounds here. We've got 3,000 pounds here. Oddly enough, 1,000 here and 4,000 here. So now those 0-point loads actually have forces in them. And I want to calculate the force in this. So we could do the whole structure, start at one location and start to solve for these forces. Or we could use method of sections. I'm not sure it's necessarily one is easier than the other in this situation. But let's cut this right here at this section. I've got this thing cut. Let's put our forces back in. Our forces in, actually. We've got a force there, force here. I'm drawing all these as tension, even though undoubtedly some of them are not tension. But that's just going to mean I'm not going to have to worry about figuring out which are in tension and which are in compression. It'll all come out in the wash. This is force FB, and this will be force AB. Okay, so, well, I'm looking for this EB guy. So why don't I get this force? This is ED, not EB here. It's heading towards D. Why don't I find this force ED off to the side here first? So I notice that all three of these bottom forces point at B. And so I can isolate everything, all the unknowns except for one, if I do that. So sum of moments about B equals 0 equals. So this 1,000 actually isn't in the picture anymore. So I have there's actually a 1,000 here. Is that in the original? No. There should be one in the original though, of 1,000 here. So I've got 3,000 times the moment arm of 2. And then I can sum these forces and get a resultant. So I've got 3,000 with a moment arm of 4 here. And then I've got this FED heading in a negative direction, FED, with this moment arm, which we're going to have to calculate. So if this is distance of 4 and these are 30, that makes this 60 up here. But opposite is what I'm interested in over adjacent equals tangent of 30. So 4 times tangent of 30 should equal that then. So 4 tangent of 30 is the moment arm. I moved this over because the FED is at an angle here, and I need the component that is here. So this is actually cosine of 30 times the tangent of 30, which is going to be 4 times the sine of 30. So this is just going to turn into 1/2 then of 4, or 2. And then 3,000 times 4 is 12,000 minus 6,000 is 6,000. So that'll essentially be 6,000 over 2, or 3,000. And it's going to end up being a negative 3,000 newtons. So that calculation was for section AA here, the free body diagram I drew for that. Now let's continue on. I think at this point, if I want the force in EB, not EEB, but FEB, then what I could do is look at this joint with 1,000, and I'm going to have this still point in this direction. And we're going to have this point in this direction. This is the force in FE. And then this is what we're interested in, the force in EB. So here's a free body diagram for E. So now we're going to talk about joint E. So summing forces in the x direction, I've got force ED cosine of 30 minus force FE times the cosine of 30. Of course, these cancels. So force ED equals force FE. That's kind of like apparent based on that chart. Now for some forces in y, I get minus 100, or 1,000, minus force EB. And then I've got these two guys here, and both of them point down. So we got minus, and they're both equal. So it's 2 times the force in ED slash FE. So 2 times this force times the sine of 30 degrees. Well, I saw up here these were the same, and from up above, that was equal to minus 3,000 newtons. And so half of 6,000 is 3,000 minus 1,000 equals 2,000. And that's the force in EB. So ED is in compression, FE is in compression, and EB is in tension.